it may have gone back 2,000 years ago, and the Great Wall of China is still standing because they used reinforced technologies. But I think that the concept of soil reinforcement as we know it today was, let's say, reinvented in the late 60s. But much of the initial application was in earth retaining systems. So when we design a retaining wall, we typically use concepts of limit state. We design a wall so it doesn't collapse. And when we're dealing with that, we really care about tensile strength of the reinforcement. And we want to quantify what are the conditions that will make a wall and a reinforcement break. And then we step back and we say, okay, we want a factor of safety. That's very different than when we are dealing with a pavement system. As you may know, we are not designing a pavement. Actually, we're designing a pavement so that it will fail. If we design a pavement so that it doesn't fail, it's a bad design. So we design pavements so that they do fail, but we do it so that we minimize excessive distress. So this is a serviceability design. And it breaks my heart when I see specifications specifying reinforcements for bases that specify a tensile strength. By the time that those reinforcements reach their tensile strength, the pavement is long gone. So, but to be very honest, that's what we have inherited from learning how to use reinforcement. So those are the type of mechanical properties that we have been using. While when we are dealing with pavements, what we really need is to understand relevant material properties, maybe deformability properties, under small displacement conditions or small strain conditions. But it's very tricky. It's very, very tricky because we really are dealing with a composite. We're dealing with a soil reinforcement interaction. And if it is hard to quantify failure or strength, or it's even harder to quantify deformability. But there has been a lot going on why there is a fact. If we do place a reinforcement in a base, the performance will improve. So that is a fact. We are trying to understand why it is improved, and consequently we want to quantify and incorporate that into the design. There has been a lot of discussion on what are the mechanisms that make a reinforcement work in a base. And these are two of the proposed mechanisms. One mechanism says the following. If we have a base, granular material, and we have a reinforcement, then with the deformations we will have a membrane effect. So that we will develop tensile forces within the reinforcement, and the vertical component of those tensile forces will help in improve the performance of the pavement. There has been another theory that says a different story. It says, well, if we do have, do we have a pointer? Yeah, that would be great. If not, don't worry. No. If we have a reinforcement, without a reinforcement, if we have a failure surface, a bearing capacity, they treat this as a bearing capacity problem. So if we have a bearing capacity problem, it's really a shear failure problem. So if the failure surface wants to go in a given direction, and then we put a reinforcement and we modify, then we modify the failure surface essentially by forcing the failure surface to go in a different direction, we're increasing the factor of safety. Now, while these are two, I would say, valid theories, they are valid perhaps for unpaved roads. It turns out that if we are dealing with a paved road, by the time that we mobilize the deformations that are needed to really come up with meaningful membrane forces, or even to mobilize the bearing capacity, the pavement has been long gone. So there is consensus among researchers, and I would be very curious of the researchers that are in here, I'm pretty sure that you agree, that the mechanism that really makes this system work is a third one, which is a mechanism that has been identified, has been defined as being lateral restraint. And what this does is essentially it says that your pavement, you design pavements much more than certainly I do, but we want stiff system. Well, all we want is to add a stiffness. So with this lateral restraint mechanism, what it does, it says that essentially what the reinforcement will do is will prevent or will minimize the intention of the base. With the traffic loading, this base will try to move laterally, distend laterally. The base will lose confinement. And consequently, what this does is that the presence of the reinforcement, what really does is that minimizes this tendency to the base to distend laterally. If the base distends laterally, essentially we lose confinement. If we lose confinement, we lose stiffness. If we lose stiffness, we have a lower performance in the pavement. So if this is the mechanism that makes this work, then what our research team is saying, do you know what? Then we have a case. Because why in the past, many of the research that has been proposed to come up with the properties that makes this work have focused a lot on traffic loading, dynamic loading. What our research team is saying, I'm not going to say that dynamic loading doesn't matter, but the way, if we all agree that this is the mechanism, thank you. All right. If we all agree that this is the mechanism, this is what we envision that happens. The traffic loading is there. We're not going to ignore it. But the traffic loading is inducing permanent deformations. The permanent deformations on the base are the ones that are pushing the reinforcement laterally. But it's not that these lateral deformations are cyclic. The load that causes these permanent deformations is cyclic, but the permanent deformations are monotonic. The pavement doesn't swell and shrink, swell and shrink. It advances, small, millimeters. But if that is correct, then we said, you know what? Then we've been looking at the wrong parameters. Forget about dynamic loading, which has made our life way too complicated. Let's simplify it. We're going to deal with monotonic loading, but still monotonic loading under confinement. And that still makes it, adds complexity to this. So the new property that we're going to be focusing on is the following. Is the stiffness of the soil geosynthetic, we've been changing the names, I would call it now, of the soil geosynthetic composite under low displacements. That's the property that we're after. It's not the stiffness of the soil, it's not the stiffness of the reinforcement, it's the stiffness of it's not an interface, because we're going to get to see that really it's not the stiffness of the interface. Maybe the best way to describe it is the stiffness of the interaction, if we can say something like that. We have recently relabeled it the stiffness of the composite. And it's under low displacements. And for sure, this property matters. What we're not sure if this is the only property that matters. But for sure, this property matters. So what these tests involve is monothonic loading, which, by the way, this is the main difference with many of the previous tests, where we do not care about dynamic loading. It's monothonic loading. We're going to get to see that initially we didn't use a conventional frame, but right now we're making it easy for labs to implement it, so we have shifted into a conventional frame. And we are doing this using a comparatively expeditious procedure. So not only we want to understand this, but this is mainly funded by the Texas Department of Transportation. They want something that can be done in practice. So I'm going to walk you a little bit through our process, and we have been through several generations of this equipment. The first one, we said, we got it, and we showed it to them and said, forget it. We're never going to do this test. So I'm going to walk you through different stages on this. But, before I tell you about that, let me do a little break for commercials. Let me tell you a little bit about the IGS. The IGS stands for the International Geosynthetics Society. And the core purpose of the IGS is to provide understanding and promote the appropriate use of geosynthetics technology throughout the world. I'm given a little bit for granted that you know what geosynthetics are, but these are polymeric materials that are mixed with soil and rock to fulfill many different functions. The function that we're dealing with in this presentation is reinforcement. I will highlight that it's very important that we are promoting not the use of geosynthetics. You do not need to use geosynthetics always. We promote the appropriate use of geosynthetics. And that means recognizing that these are not commodities, these are engineering products, and as such, we need to test them, we need to design with them. This is our world. In red are the countries that have chapters of the International Geosynthetics Society, including the North American chapter. By the way, if you are a student, provided that you get the signature of one of your faculties, you can become a member of the IGS for free and have access to many different benefits, including 2 high-quality journals that you get access to them directly for free as a member of the IGS. And if you're not a student, I think that for North America it's just $75. So it's one of the cheapest memberships that you can consider. You will have access to information, in this case, on paved roads, erosion control, hydraulic projects, walls, other strong interaction with practice. What you have in here, this is the winner of the 2010 project picture competition. This is a lined baseliner of a waste containment facility. Look at these steep slopes. This was in Hong Kong. This was the picture that won the competition in 2010. We just finished the next competition, and this is the winner in 2014. This is a lining of a mine waste containment facility in Mexico. In addition to this interaction with industry, you have a lot of access to information about members, and these are the members in the USA, starting with A. Here's Professor Okadi. I'm Z, so you're never going to find me here. But in addition to that, you have access to geotextiles and geomembranes and Geosynthetics International, 2 premier, among the geosynthetic, not the geosynthetic, the geotechnical and geological category of journals. This ranks number 2. This ranks number 4. Very, very high quality journals. So if you're not a member, visit www.geosyntheticsociety.org. All right. After the commercials. Okay, so what I'm going to show you now is because when we want to come up with the interaction, the stiffness of the interaction of a confined reinforcement under small displacement. This is a mouthful, but we want even more than that. We want that all these be characterized with one parameter. Because when we start using functions and multiple, even when we deal with shear strength, if we use C and phi and you want a specification, you're lost. So that's why we want a lot. We want not only that mouthful property, but we want it characterized with one parameter. Give me one number and I'll tell you if this interaction is stiff or not. So that's what we're going to try. So what I'm going to show you now are some assumptions, and I recognize that these are assumptions. But if these assumptions are valid, then the math becomes simple. And if the math becomes simple, I come up with a single parameter to characterize it. If these assumptions are not valid or not accurate enough, then everything that I'm telling you is still correct. The only thing is that we will need a more complex function to characterize it. But in order to come up with this one parameter, when we characterize the soil reinforcement problem, essentially we're pulling out a reinforcement and we're tensioning the reinforcement under confinement. And that interface, and so what we really want is some characterization of this interface between the reinforcement and the soil. And there have been many models that can characterize this interface, linear, perfectly plastic, and this is a series. We can become complex. We can add some complexity on how to characterize this interface. In addition to that, we also need to, this is a composite, so it has a tensile element. We need also to characterize the tensile properties of that reinforcement. And could be linear, nonlinear, different ways in which we can characterize it. And we tried many of these. We're going to come up with a differential equation. And depending on how the constitutive models that we use for both the reinforcement and the interface, we can come up with complex differential equations that we can only solve numerically, or very simple differential equations. So we tried different combinations, and we learned that a very simple combination, very simple characterization gives us very, I wouldn't call it accurate, I'm going to call them acceptable results. So if we can make life simple, why not? So we're going to choose simple. We need to make our problem as simple as possible, but not simpler. So, yeah, and to make it as simple as possible, the characteristics of the interface shear is we're going to assume that these are rigid, perfectly plastic. And for our tensile properties, we're going to consider that this is linear. Again, I'm not claiming that this is true. I'm making it upfront. These are hypotheses. We will be able to check if these hypotheses are acceptable. Not accurate, acceptable. So if we make our interface shear a rigid, perfectly plastic, essentially we're dealing with this problem. At the interface between the reinforcement and the soil, we develop shear, and whatever the displacement is, that shear has a constant value. Constant value. It's going to depend on the confinement. But for a given confinement, for a given condition, it's not going to be a function of the displacement. That's what we are assuming. But if we assume this makes our life a little bit, well, makes it easy, because if we're pulling our reinforcement, this is our reinforcement. And this is the length of our reinforcement. So if we are pulling this reinforcement, essentially what this is telling us, if we use this assumption, that the reinforcement for a given length is going to develop a constant shear. And once we satisfy equilibrium, there's not going to be shear at all. So it's a black or white. So a certain length that we're going to call L prime, effective length, is sheared. The rest is dead. That's what we're assuming. But if that is correct, essentially what that means is that as we pull on a reinforcement, we pull, there is a little bit of a small shear zone. We pull more, there's a bigger shear zone. We pull more, there's a bigger shear zone. This is in equilibrium. So we even know what the length should be. And this is how we're going to characterize the interface between the reinforcement and the soil. Okay. In addition to that, and this is a controversial assumption, I must recognize that, but we're going to check if this is acceptable. The other assumption, which is I think that more generally accepted, is that at least for the level of displacement of interest, which is small displacements, the relationship between reinforcement, tension and displacement, or tension and strain, is linear. So essentially what we're assuming is this. This is the tension in the reinforcement. This is the strain in the reinforcement. The slope, which we call J, is not really modulus because this is tension per unit width, is a constant. And I'm calling it, typically you would see this as being called J, the stiffness. I'm going to call it JC for confined stiffness. So we're assuming that this is linear. We are not assuming, we're relaxing the assumption that this stiffness is the same under the one that we would get under unconfined conditions. So whatever the stiffness is under confinement is constant. So essentially the tension will be the confined stiffness times the derivative of the displacement. Well, but now it's a matter of just putting together equilibrium. So for this to be an equilibrium, we have a very simple differential equation at the element level. And using the two constitutive assumptions that we have had, the tension is linear with the strain, and the shear is a constant. And ultimately, we come up with a differential equation. That's it. That's the differential equation that solves our problem. To be very honest, this is not new. Many people have come up with this differential equation. Not necessarily with these constitutive assumptions, but these are very simple, so you probably will see it. But we're not done, because once we have a differential equation, we still have not solved the problem. We need boundary conditions. And what I'm going to show you, even though it ends up being, of course, it needs to be this way, we have not seen it in the literature yet. Because for boundary conditions, typically the assumptions that you will see in a problem like this, you have a boundary condition here, a given force, and you have a boundary condition here that is, let's say, zero displacement or zero strain. That's what being typically, and you end up with equations that do not look good, and the validity of the equations has been questioned when compared to experimental data. What we are assuming, because of our assumptions, essentially we're going to use a moving boundary. So essentially we're going to limit our domain to the active length. So our boundary conditions are these two. So we have a boundary condition here, and the boundary condition not at the end of the reinforcement, at the end of the effective length of the reinforcement. And at this point, the tension is zero and the displacement is zero. But if we do this, so this is not what we're doing. This is what has been typically done. This is what we're doing this. But if we do this, life becomes so clean, because essentially this is it. If our assumptions are acceptable, then what this means is that the tension in the reinforcement squared as a function of x is linear, is directly proportional to the displacement at point x. And the constant of proportionality is a function, and that's why this is truly a composite behavior, because this constant of proportionality depends on the stiffness of my reinforcement and on the interface shear characteristics, and it kind of makes sense. So if you have a reinforcement and you have, let's go to an extreme, and if you have rubber band, it doesn't matter if this displaces a lot, it's not tensioning. So this property is important. On the other hand, if let's say that it's very, very stiff, but it's Teflon lined reinforcement, then it shears, then it's not going to work. So it really intuitively makes sense. But we can do better than intuitively. We can go to the lab and check if this makes sense. So essentially, the math tells us with important assumptions that the square of the tension at any given point in the reinforcement is directly proportional to the displacement at that point. And this is a constant that we're going to call it the stiffness of the solid geosynthetic composite. And with that, we anticipate that it's going to tell us a lot of how pavements are going to work. The interaction is going to work under low displacements, and consequently, we'll have a lot to say about reinforcements that do work and reinforcements that do not work in a pavement system. So this is it. This is essentially what I've just told you. All right, so let me give you some predictions. So if the math is correct, essentially what we're saying is that we have the tension squared versus displacement. This is a straight line. and the slope of that straight line is the parameter. So that's what we wanted to get. Not only we wanted the stiffness of the solid geosynthetic composite under low displacement, but we wanted more than that. We wanted to characterize this with one parameter only. And if this works, we get it. But if this works, essentially what we're saying is that the relationship between tension and displacement is a parabolic relationship. And even we get everything. If this works, we have everything, because we have the shear along the reinforcement, and we have the tension along the reinforcement, and we have the strain along the reinforcement, and we have the displacement function about the reinforcement. We have it all. And with this, we can design. So let's go to the lab. So we want a stiffness parameter of the composite, but under confined conditions. There is a test that I'm not sure if you have come across. How many of you are familiar with what is a pullout test? Okay. So a pullout test has been used extensively. Essentially, you have a reinforcement, you sandwich it under with a soil, with the real soil, and you pull it out. And you simulate that, because that's the real mechanism that, let's say, in a reinforced wall, that's how the tension will develop in the reinforcement. Now, there has been tons of research on this, how big this system should be, and how the clamping, how it should be, and how to make sure that the stress distribution is uniform. So, but all this has been done with the purpose of obtaining what has been called the pullout resistance. So we're going to capitalize on all these discussions and ASTM committees that came up with the right equipment, but we're going to use it for a different thing. We're going to use it to get stiffness. So we're going to look into displacements and not only strength. So we're going to measure not only the frontal load, which is what typically we measure in a pullout test, but we're also going to look at displacements within the reinforcement. And to be very honest, that has been done in the past, but mainly with the purpose of defining whether you have reached pullout resistance or not. And the third thing that we're going to pay very important attention to is we're going to monitor the displacement within the reinforcement at different points, but we will pay particular attention to the point in which we have the onset of displacement. So if we're pulling out, at some point, we're waiting here. This is my point. I'm pulling here. And I'm pulling. At some point, this point will start moving. That moment, we need that moment. We need to identify what is the onset. What is the load that causes the onset of displacement at different points along the reinforcement. And with that, we can define the properties that we need. So this is our reinforcement, and we have, essentially, these are telltales. So this is under confinement, and we're monitoring we're applying this load, and we're monitoring the displacements at different points. So this is a cross view, this is a plane view. So we're applying the frontal tension, and then we're going to monitor what is the displacement at different points. We're going to infer, we do not measure this, we infer what is the unit tension in each one of those points. And this is the test that we're going to do. This test, again, we have modified what is called a pullout test device. That looks, in cross-section, looks something like this. This is not exactly how, we have modified the normal load application system, but the idea is that if this is the reinforcement, we apply the loading here. This is a big scale test, or at least for what conventional tests are in geosynthetics and in geotechnical engineering. This is a comparatively big test, big box. We apply the loading here, and we monitor the load internally with telltales at different stages, and we do it at 5 different locations. And this is what the pull-out box looks like. So again, so this is how it looks. Tension, displacement. We're going to pay particular attention at what is the tension at which, at different points, we start mobilizing that displacement. This is a view of the LVDTs at the back of the Pullout box to monitor the internal displacements, and we get curves. And this is essentially, if we get that curve, this is essentially what we would like to get. One possibility would be just if we plot the tension versus the displacements and at different times, and we plot tension square versus displacement, and we get a straight line, then we're happy. If we don't get a straight line, we need to go back to the drawing board. So essentially, we would be happy if we get something like this, but even more. What this formulation is telling us is that the displacement, if we get the displacement at this point, 1, we are going to get the same slope if we base it on the displacement of point 2, and the same at displacement point 3. So really, to be really happy, not only we need a straight line here, but we need that each one of the, essentially when we do a test like this, we're getting 5 curves. And all those 5 curves, if our assumptions are acceptable, need to be the same. And even more, we're dealing with stiffness. And I think that I was quizzing Professor Tutumbler on what is an acceptable scatter for stiffness. Tell me, because when I show a scatter for shear strength of 5%, they say, oh, that's terrible. But what is an acceptable scatter for stiffness, for moduli? You tell me, what is acceptable? Unbound materials. Great. So that's what I've heard that, but it's not written anywhere. Where did you get it? I need a quote. Thompson? Okay. Can I get that from personal communication? All right. So I need a quote. We are around that. We're 25%. And what I hear is that, this is my friends in the transportation group at UT. They tell me that in reality, if you get a scatter of 100%, you're happy. So we're getting 25%. So we are happy. So essentially what we need is not only needs to be linear, but needs to be the same. And honestly, within one specimen, we get five curves. This, if we get this, we're happy. If we don't get this, we're not that happy. Yeah. The load? The load, this T, okay? Correct, is at a point. Very, very good point. If we know, if our assumptions are correct, let me go back. That's an excellent question. And I'm here. If these assumptions are correct, then the tension at any given point, that's why we need the onset. The tension is 0 at the time that we apply a load in which we initiate movement at that point. From that point on, the tension at that point, if these assumptions are correct, is going to be the additional tension that you keep applying at the front load. Make sense? And that's a very good point, because when what we're plotting here, we are assuming that that is correct. If not, we cannot plot tension. Here is not the tension at the front load. It's not the frontal tension. It's the tension at a point. And the tension at a point, in order to get it, all this needs, either everything works or nothing works. Needs to be a straight line, and we'll know what the tension is if all this fits in place. Okay. So essentially, our current protocol is that we will measure the displacement at 5 locations within the reinforcement. We will measure P, the frontal load, not the load at each point. Yes?
I'm just wondering, because it seems like the application of the for pavement.
Correct.
The procedure is assuming that the load is applied in one direction.
Correct.
Actually, very important way is the pavement. You're going to have these tensions in both directions.
Correct.
How does one figure?
That's a great point. Two answers to this. Answer number one. In Texas, this is mobilized in one direction. And I'll get back to you, not because Texas is that different. The main application that I'm going to focus on is going to be on pavements on expansive clays. And I'm going to tell you why. Really what matters is the tension in the cross-machine direction. But we are going a step further, and we are saying what we have just discovered for the design of reinforced bases on expansive clays is also the property that we need for traffic. So, and now it gets a little bit on whether you want the actual property, because you're going to do a, let's say, a deterministic design. So you really need the actual stiffness, or we're going to use these for specifications. Then what matters is not that much the actual value, but some correlations, or even in a mechanistic empirical approach, what we really need is not the actual value of the property, but a good index of that property. So I cannot give you the answer to that. I would say testing that, but what you're asking is valid not only for pavements, it's valid for reinforcements in general. There are some studies that would argue the following. If you're testing in one direction and you're under unconfined conditions, then you're going to have necking occurring, and the tensile properties that you measure under unconfined conditions will vary significantly with how wide your specimen is. Once your specimen is wide enough, then you're essentially working, you're getting rid of that, let's say, let's call it a Poisson effect, or let's call it a lateral effect. Some others have investigated this even further, and they say, do you know what, this matters a lot when you're testing materials under unconfined conditions, but when you are under confined conditions, even if the specimen is not that wide, then it's the confinement that will prevent this necking. So I cannot give you a full answer to that, because I could only give it to you if we do the right testing. I could say that there is good evidence that this could be good enough if you test it in one direction and you minimize or prevent the necking. And in principle, you do that by adding confinement to the specimen. But very good point. All right, because if, coming back to here, if we do this and if we get this relationship, and if, many ifs, if we get this relationship, and if this relationship is a straight line, and if all the different points give us the same straight line, then we're happy. Because all we need to do to obtain this parameter is we get this slope as t squared over u, and that's it. I'm going to skip this because there are other ways. We tried getting this in different ways. A different way would be to predict. If you remember, this KSGC was really the product of two parameters. Was the confined stiffness of the reinforcement, and the other is the yield shear. There is a different way. With the same data, we can get it in a different way by the product of those two. Or we can even go a third way, which is essentially forget about this slope. We now, and this is potentially getting a little bit rid of what you had mentioned on or implied, that you need the actual tension that you're not measuring. So potentially we can feed a parabola to a displacement curve, to the displacement function, and instead of getting one property at each point, we need all the points, but we feed one parabola and we do get the parameter, the stiffness. And we have tried all three, and they give very consistent results. It's the same data set. Currently, the one that we are proposing, because it's the simplest, is just plot it and get the slope of a curve, and that's how we are getting it. But in any case, there could be different validations, but the point is the following. So if we do this test, And this is what the test may look like. So this is the specimen. These are the telltales. We measure the displacements at the end. We're going to pull it from here. We're going to monitor the load at the front. We're going to monitor this displacement at each point, and we're going to monitor what is the load at the point, at the time in which the displacement is initiated. This is a curve, typical curve that we get. Frontal tension, clamp displacement. This is also data that we get. Frontal tension, because we do not have the tension at each point. This is what we have, the frontal tension, clamp displacement, and displacement within each point. And this is a different way of looking at it. So this is the frontal unit tension versus the LVDT readings. So for a given clamp displacement, we have the unit tension. For a given clamp displacement or time, we have the LVDT readings. This is what the curves look like. They're nice looking curves. Well, now is the proof. So let's plot it. This is raw data. Let's plot it into the T-square versus U field. And this is what we get. Unit tension versus displacement. Or if we get unit tension squared versus displacement, we're happy. We get very close to a straight line. And if we get, here we have different curves from the same test. And they are, because we're getting the displacement at different locations, this is the LVDT that is at the very front, so it will have a larger displacement. This is the LVDT at the very back, so only a shorter displacement. And this is how all of them look like. This is how all of them look like for this particular test. This is a very nice looking test in the sense that in some other cases we will have higher scatter, as the one that I'm going to show you, but all of them give us essentially a straight line in this space. So we can argue about the scatter, but not that much about the validity or the acceptability, not validity, acceptability of our assumptions. They all give us unit tension squared versus displacement, a straight line. Again, and when you get the slope, the numbers can vary significantly with a little bit of change. They look good, but when you get the numbers, you say they're awful. And so that's why we're within 20%. And this is the repeatability within one test, 5 data points in one test. This is the repeatability across multiple tests. KSGC 23 for test 1, different test KSGC 21, different third test KSGC 21. So we have gone a long way to not only be able to come up with the prediction, come up with the equipment, evaluate the repeatability, and I can say, okay, we're not there yet on saying this is how you use it in design, but if what a property that you want is the stiffness of the composite under small displacements, we're confident that this is either it or a very good basis for it. So we went to TxDOT and we said, here it is. And they said, lovely, we're never going to use it. Why? Because it's too big. It takes 2 days to get one data point. We want something quick, fast, that we can put into a specification. So what I'm going to show you that, and I'm glad that they did that, because we went back to the drawing board, but now already knowing what we wanted to get, but we wanted to modify the experimental setup. And instead of doing this, we are now modifying it into doing this. Same idea, same idea. But instead of a big box and that we pull horizontally, we're going to have a box that is large enough that fits into a conventional load frame. Are you familiar with the tensile test on geosynthetics? Why with tensile test? Same frame. Same clamps. This is what is called the roller grip. Same clamps. If we do a tensile test, here's a clamp. This is a grid. Here you would have another clamp, you apply a tensile load, you do a tensile test. Here what we're going to do is we're going to replace this lower clamp by a pull-out, mini pull-out box. We sandwich the second end of the reinforcement. And it's still a tensile test, which a pull-out test is a tensile test. But this is under confinement, so we apply with air pressure, we apply confinement with the bladder. It's confined under the confinement of soil. And we measure the displacements within the reinforcement. Actually, we measure five different points. A big question for this is has been, and this has been going on forever, is the boundary effects. Boundary effects. But we concluded two things. First, when we are, everything that we have learned about boundary effects on pull-out tests is based on conditions at failure. And the effect of the boundaries once you reach large displacements is significantly more relevant than for the area of interest that we have in here. That's one. And second, even if what we get is affected by the boundary conditions, chances are, and this is a hypothesis, chances are that the effects will be systematic. So that when we the ultimate goal is to compare geosynthetic A with B with C with D. So chances are that the properties that we will get will still be comparable among themselves, even if the results are affected by the pull-out, by the boundary conditions. But to be very honest, we did an extensive, and this will depend also on the particle size distribution and all that stuff. But the tests that we have done so far, at least for the purposes of calculating or predicting the stiffness, have been very good compatibility between the results in the large pull-out box and in this small pull-out box. Much faster. So we're replacing this with this to obtain the same parameter. This is how what the system looks like. A conventional load flame, burnt orange. That's part of the specification. This is the typical grip. That's a grip for tensile tests. No lower grip. Instead of a lower grip, we have a pull-out box to confine the specimen. Data acquisition system. Everything fits very nicely. And essentially, this is what it looks like. We're monitoring 5 points, displacement at 5 different points. And this is the procedure. So we line the internal, because we minimize the friction by lining the boxes. So even though there is a smaller volume, we minimize the friction. That's placing the geosynthetic in the box. We have finished the second portion of the box. This is the air bladder that will apply the confining pressure. That's the box in place. By the way, when we run a pull-out test, we're also monitoring what happens with this portion. Do you know why? Why would we want to do that? Two tests, yeah? We monitor this portion. Yeah. Yeah, so we get 2 tests for the price of 1. So we get the pull-out response, and at the same time, and this is an unconfined tensile test as well. So there's strain in here. We monitor the strain of the unconfined portion, and we get the tensile strain response of the unconfined reinforcement, and we also monitor the stiffness of the composite. We are kind of concluding, but not yet, we're not there yet, that what we initially called the confined stiffness is very close or very often the same as the unconfined stiffness that we're obtaining. That will be later on. Then this is a view of the upper portion of the box. This is a view of the lower portion of the box with the LVDTs to monitor the telltales at the different points. All right. So let me show you some results. We're testing this in geosynthetics are anisotropic materials. So the testing in the machine direction is not necessarily going to be the same properties in the cross machine direction. We're testing them both. And these are some results that I'm particularly interested because we have some field evidence with these results. Amongst, I didn't sanitize this. Yeah, that's okay. Forget about this. This was supposed to say geosynthetic ABCD. But this is what we're getting in terms of stiffness of different products. This is normalized stiffness in relation to one given product. This is definitely, this is kind of, these are many different products because this is what we're doing right now. This is the testing program that we're doing right now. If we're going to use this for design, we need to test the actual base with the actual geosynthetic. And that would be what we need for design. But we're never going to do that. We may do it, but essentially what we need for design is to compare different geosynthetics for whatever base the contractor ends up choosing. So the ongoing testing program that we have going on right now is essentially the idea is to identify a standard granular material that we will use as a reference to calculate the stiffness of different geosynthetics and validate whether by changing within parameters the grain size distribution, we still for sure are going to get different numbers. But are we getting still the same, let's call it ranking? Product A works better than product B, works better than product C. That's what TxDOT wants. And it's great for specifications. I could say that it's also good for design, maybe shy of what we really need for an actual deterministic design. In that case, we would need the actual property of the actual geosynthetic with the actual base. So that's where we are right now. That's ongoing projects. I'm going to still get you to the field, but let me divert a little bit because that I showed you generation 1 and I showed you generation 2. Let me show you generation 3. And by the way, TxDOT is very happy with generation 2. So that's what we have a draft specification for that. We are doing a major testing program to validate essentially two things. One is the sensitivity of the results to different base materials or granular materials. And two, the correlation, believe it or not, this has been used in the field a lot. So we can go back to the field and validate the field performance ranking based on field performance with a ranking based on KSGC. That's where we are right now. We're diverting as well because we say, well, but we really didn't want to go from a very sophisticated equipment to a practical equipment. But we're taking this one step farther, and we are getting into, we're getting into transparent soil. So this is what I was talking to Errol about. Do you know what? Because we are dealing with a smaller volume, Dr. Tutumle has been working a lot with the discrete elements and trying to see what happens. And let's model this Geogrid. So I'm going to give him a present. I'm going to say, do you know what? I'm going to, instead of doing this confinement with gravel and measuring the displacement at 3 different points, and we're so happy that we measured the displacement at different points, I'm going to give you the displacement at every point in the grid. And not only at the nodes. Do you want the bending of the transverse strips? I'll give it to you. Do you want the stretching of the longitudinal grips? I'll give it to you. Do you want how So if all of them work the same way or there is scatter, internal scatter, I'll give it to you. And the way to do it is with transparent soil, which is doable. And this is it. This is a proof that it's doable. So what is in here is a similar box to the one that you had before, but now it's a transparent box. And inside that transparent box, it may look that there is nothing, but there is. There is transparent soil that is under the same confinement that we had before. And even better, if you look at the side view of this box, this is a Pullout system, this is the same thing. So now, these are markers. No, and this is the geosynthetic. And I can capture not only the deflections on the grid, but also the shear band. There has been a lot of discussion on this composite behavior, and that has a lot to do on how the reinforcement, how the shear distributes in the vicinity of the reinforcement. So I'll give it to you. And this is the same thing. This is the same box, but looking at it from the side. So this is the side view. This is the camera. This is the camera. So this is looking at this side. This is the box in here. So we can track the displacement of the confined grid in here. Well, it's not magic. It's a little bit of physics. It turns out that if we get a special aggregate, which is fused quartz, high-quality fused quartz with little impurities. And we measure the refractive index. And we come up with, to the third decimal point, with a mixture, a liquid, and that's an oil, mixture of oils, so that we have the very same refractive index as the fused quartz. That fused, that becomes transparent. So it's not really a granular material, it's an artificial granular material, but for the purposes of understanding the soil reinforcement transfer mechanisms, I think that this is very insightful. Just an example of two tests. This is one type of grid. It's called the triaxial type of configuration. This is a more conventional biaxial type of configuration. This is before testing. This is after testing. This is before testing. This is after testing. This is before testing. This is after testing. And we're playing with digital image processing in order to manage this huge volume of data. We want the bending. We are trying to capture the bending of the transverse reefs in order to translate how that bending relates to the load that is being carried by that node. We also need the rotation of the joints, if any. We also need the stretching of the reefs. We also need the scatter of those displacements. But that's not part of the, that's beyond TxDOT. TxDOT is not interested in that so far. All right, so let me wrap this up very quickly. And I'm gonna, okay, this is, looks okay. Our initial hypothesis seem okay, but what is the relationship with the field? Is this relevant? So that's a very difficult question. As you may know, getting field performance on a serviceability basis is very time-consuming, very difficult, very subject to significant scatter. So let me walk you through what happens in Texas. Texas is the state that uses soil reinforcement. No, let me put it this way. Basal reinforcement has been used across the US and the world, everywhere in the world but in Texas, for two main reasons. Reason number one is because you want to decrease the thickness of your expensive base and keep the same design life. That has been a very good basis for design. There's a second reason. You want to keep the same thickness of your base, but you want to extend the design life. That's another very good reason that worldwide has led to the use of reinforced bases. Texas is the state that uses basal reinforcement the most, and it's for none of these two reasons. The only reason, to the best of my knowledge, that many of the districts are using basal reinforcement is to mitigate the problems associated with expansive clays. So let me tell you what this is. This is the US. And you are safe because you are here. So, but if you are in the blue area, which is all the central US, southern US, that's high percentage of expansive clays. If you are in the red zones, which by the way are the ones that are taking the US out of the recession, because these red zones means shale, and this means energy. And that's why North Dakota and Texas are being what they are, because fracking, you may have come across that. And with the problems that that induces in transportation, where you have problems with fracking is in this central US. Now, it turns out that, but if you have red, essentially, for other than for energy production, stay out of there, because we have a serious problem. But the problem, it's not that easy, because if we have a closer look at Texas, this is Dallas, this is Austin, this is San Antonio. So the design of Texas, the design of the major cities of Texas is, let's look for the worst soils, and let's put the major cities along. This is the Eagle Ford Formation. So we do have a problem, and we cannot get away from it in Texas. And what is the problem? Do you know that some would say that expansive clays are a natural hazard? And this is data, real data from costs. According to insurance companies, the costs in infrastructure due to expansive clays per year by far exceed the costs of all other natural disasters combined per year. And all other natural disasters include flooding of Katrina, earthquakes, hurricanes. All natural disasters, if you consider expansive clays a natural disaster, the costs, they are not catastrophic. They are not life-threatening. But in terms of costs, it's potentially the most relevant natural hazard, certainly in the US. So because you have problems in buildings, you have problems in roads. And I'm going to go very quickly. A separate life of me is doing research on unsaturated soils. Let me give you only 2 slides on this. This has nothing to do with, it has to do with expansive clays. So what we're doing as well, characterizing expansive clays is not easy because it takes a long time. So let me tell you that we are doing it at UT by spinning, accelerating the swelling process, by accelerating flow process into expansive clays. So if we have a sample and we spin it under 200 Gs, we accelerate the flow process by 200 times squared. So we're getting, this is the swelling of a typical curve of the Eagle Ford Formation. We are talking about 25% swell, 25% strain. That means that if you have a layer, it will depend on the confinement, but if you have a layer of that is 4 feet thick of clay under your pavement, the potential for this layer to expand is 1 foot up or down. That's not good. We're talking about 25% strain. 5% strain is huge. We're talking about real soils with 25% strain potential. And what does this do for clays, for pavements? There has been a lot of discussion on this, but we're very convinced that this is what happens. when you have a pavement and you are it's under expansive clays, then your shoulders will, during the wet season, will heave. The center line doesn't change that rapidly, the moisture. So the shoulders will get wet very quickly and will heave. During the dry season, the shoulders, not the center line, will shrink. So essentially, your pavement will flap. Will not fly, but will flap. And essentially, the damage due to in the presence of expansive clays is very characteristic. You're going to have longitudinal cracks, and these are extremely characteristic. They have nothing to do with traffic. Very often they occur before even traffic, the road has been opened to traffic. And if you are driving by Texas, typically in low volume roads, and you see this type of damage, that's expansive clays. And this is another cartoon version of what may happen if you have infiltration from the shoulder into a cross-section of expansive clays. The main problem, do you know what happens? 2011 was a record dry season. It's not, during the heating, it's not that much of a problem. You're flexing the pavement in the right direction. The main problem is during the dry season. That's when the longitudinal cracks will occur. So very quickly, because I know that we're out of time, let me show you a field case, Central Texas. This field evaluation was a reconstruction of a road on expansive clays. And as part of, I'm going to walk you very quickly through many important aspects of this, because the only aspect that I want to emphasize is whether the KSGC that I've been talking about matters or not. So this section had, we convinced TxDOT to put not one or two, but 32 test sections with different geosynthetic reinforcements. And the treatment of choice for expansive clays in Texas is lime. So lime, no geosynthetic control, geosynthetic 1, 2, and 3. So lime, no lime, geosynthetics, and 4 different types of geosynthetics. 8 groups and 4 repeats of each group. So we have a sampling of 32 sections. This is what the cross-sections look like before reconstruction, after reconstruction. Some of them are lime treated, some of them are not. Low volume road. Significant monitoring of moisture changes. Okay, and this is where I wanted to get. We have been doing, at this time, by 2012, 20 condition surveys. So across these 32 sections, we have been monitoring over 7 years what are the different types of degradation that we can characterize. Rotting, alligator cracking, longitudinal cracking, transverse cracking, but of particular relevance for us, because this is the fingerprint of expansive clays, was the characterization of longitudinal cracks. We did follow TxDOT PMIS in the characterization. And these are the results. Actually, what I'm going to show you is the difference between the level of the survey. 2011 was a record dry season in Texas. So I'm going to show you the difference in performance in terms of longitudinal cracks between survey 15 and survey 18, actually survey 14 and survey 18. And these are the results. Oh, I'm going to come back to that. To complicate matters, we also had to do a very significant field evaluation to make sure that the different sections, we treat the sections accordingly to their actual soil, subgrade material. This is what they look like. And this is where I wanted to get. So this is the histogram of precipitation. And the one that I'm going to focus is this one. In 2011, this was a record dry season. And I'm going to quantify how specifically the longitudinal cracks have evolved from before to after the end of the dry season. Condition surveys 14 and 18. And this is it. This is longitudinal cracks in percentage. Essentially, what this means is that if you 20% longitudinal cracks, that means that 20% of the length of the road, either by one crack, if you put a line all crack one after the other, 30% of the longitudinal of the length has longitudinal cracks wider than 3 millimeters. That was our basis for performance evaluation. And this is our control section. And these are the reinforced sections. Multiple sections, the white ones are the average. It's very clear that the control section, all the three reinforced sections clearly outperformed the control section. This is an entire presentation in itself, but I'm going to tell you why I'm walking you through this quickly. And this is the performance, survey 14, survey 18, crack percentage. Before the dry season, we were 0% to 8%. Within the span of 12 months or so, control section went from 8% to 65%. And the reinforced sections unambiguously performed better. It's not that the longitudinal cracks are not going to be present at all. They're going to be minimized, but significantly. I could say that if the dry season would have lasted 6 months only, this could have been a very drastic difference. After 6 months, cracks started appearing on the reinforced sections. So there is an unambiguous conclusion is reinforced sections worked to mitigate problems associated with expansive clays. Now, which one is better? Well, all three geogrids or geosynthetics that have been chosen have performed equivalently. So if our KSGC has some merit, it should give us equivalent values. Let me give you one peek at the most controversial aspect of this field evaluation, which is not, because the big fight is, this is industry, so my reinforcement is better than yours, and my polyester is better than your polypropylene, and my geogrid is better than your geotextile. That's a big fight. But let me tell you, we are getting into another really big fight, because this is the comparison between control section and lime stabilized section. And it's not that easy to tell to the lobby of lime stabilizers. For longitudinal cracks, and let me be fair, honestly, if we were to there and look at rotting depth or other measures of performance, that would not be the case. But for longitudinal cracks, this doesn't work. The hypothesis behind it is that essentially you are creating a stiffer, which is good, but more brittle material. And if what we're trying to minimize is initiation of cracks, brittle is not good. But that's a different battle. The important aspect that I wanted to give you, and this is a different way of looking at the results, this is control and lime. Actually, if we have, this is control and lime, this is geosynthetics on lime, very uneven. So the presence of lime sometimes made reinforcements work not as good. This is geosynthetics, no lime. Definitely, and this is percentage of longitudinal cracks. Certainly, these outperformed by far all the other two. What this is interesting, and that's the main reason why I'm bringing all this database to you, is to say, well, this is essentially the same performance. Hopefully, KSGC could give us similar values. Oops, and I don't have it here. I think that I have it. This is the one that I should have showed you. All right. And this is how those three geosynthetics do perform in terms of KSGI. This is KSGI, and that's field performance of the same three geosynthetic products. All right. So to conclude, I'm going to say the following. An investigation was conducted to identify properties that may be relevant for design. Pullout testing was identified as a potential equipment or framework to obtain this property. And the property that we're currently investigating is the stiffness of the salt geosynthetic composite under small displacements. The results from a comprehensive experimental testing program showed the suitability of the hypothesis that we have identified in order to define this stiffness value. A new small pullout testing program device was also developed, and it shows is promising in terms of acceptability for design purposes. The values of this stiffness was identified as having good repeatability, and there is some initial evidence, and this evidence comparison between field and lab is always very difficult, but the initial evidence that we're getting in comparison between field and lab performance is that there is significant merit in using this parameter as a measure of the ability of the reinforcements to improve the performance of pavements. Finally, I could say that geosynthetic reinforcements have demonstrated to improve, and often very significantly, and this is a clear conclusion, the performance of pavements. And the state of practice is rapidly improving as new research is being conducted to identify the properties that matter. And hopefully, in addition to use it, we will be able to come up with appropriate design criteria in order to use it. And with that, thank you very much.
Thanks a lot. This is a great presentation. I know we're a little bit overboard here, but still a couple maybe burning questions for Professor Zornberg. I have already several myself, but I'll talk to him later. So.
Yes.
Were there any pressure injection line sections in that farm to market route?
Yeah, that's one of the, no. To be fair to this, in this side, essentially, and this is standard practice in Texas, they didn't do treatment of the subgrade. What they did is they lime treated the subbase of the system. So I could say that this is real data, but it is a stretch to essentially to say lime treatment does not work. I could say that there is evidences that you should be careful. So far in Texas, if you have expensive clays, you could treat the subbase, period. Now they are rethinking about that. Yes?
For the transparent soil, do you include the oil or fluid during the test to make it transparent?
Yes. So that's an advantage of us testing this pull-out system in a vertical direction. So it's not the oil, the soil matrix is under confinement, but it's very granular. So we do not generate pore water pressures, but we do have the oil in order to observe. So what we're really testing is confined Geogrid submerged in oil. We have done separate testing to evaluate the potential effect of having oil versus water, and what we concluded is that there is a small effect because there is a viscosity issue. But that has more to do with the time response of some of the displacement behavior. But in terms of load responses, it's very similar. Yeah.
Last question. Any intention to build a box for this Pullout test such that we can put in a real base course gradation, top 1 inch size? That's graded.
Say that again.
And
a big.
provide the aggregate geogrid interlock by actually aggregates interlocking in the apertures. Well, I know that's happening with sand or smaller size grains.
Transparent soil or non-transparent?
No, larger gradation, top 1
Oh,
is
yeah.
typical standard base course gradation.
Yes. The answer is yes, not in the small Pullout box.
Build a big
Let me, there is a different project.
Because you mentioned to do standard base now testing geogrid.
Yeah.
That's more like what we use for a base course. So
There is a completely, this is never going to happen for specification purposes, which the idea is essentially to test all geogrids and geosynthetics and put it into an acceptable list of products. We have a different project. Honestly, it's not for pavements, but it will make use of all this. It's an NCHRP project. Have you heard about GRS IBS, Integrated Bridge Systems? We are constructing a mega Pullout box, not with transparent soil, but with a transparent sidewall. So we will do Pullout tests and we will not see the deformation of the grid, but the intention here is to characterize the shear band that develops under actual aggregates. So it's more limited in the sense that we will not see the deflection. We still will get data points of deflection. Correct. Correct. That will be able to, we will be able to get that. We will be able to get the thickness or some measure of the shear band. We will not be able to get the deflection of the reeds, for example. But that's coming in 3 years.
Great. I think that concludes today's seminar. Again, thank Professor Zornberg for a great presentation here. So why don't you join me?